Hello class, these are our Algebra 1 notes for section 6.6. Today we are building quadratic functions to describe situations, and this is part 2. We're spending 3 days on this. So a little bit of vocabulary first. A parabola is a U-shaped curve. So these are actually the kind of graphs we've been making this quarter, well, I say this quarter, but for this unit so far in Unit 6. So it kind of has this shape to it. When we've been doing those maximizing area problems, we get this kind of graph. I'm trying to think, when we do the patterns, if we graphed our data from those patterns and the number of squares, we would get this kind of graph. So it is for a quadratic. It is the shape of a quadratic. The vertex is the point where the curve changes direction. It is also the max or min. So if I think about what a quadratic looks like, the vertex could be this point at the bottom. So if we look at our curve is going down and then it stops and then it comes back up, or if I'm looking at an upside down U shape, my graph is going up, it stops, and then it's going back down. So you could almost think of it as like throwing a ball and that motion, projectile motion. So these are what we're talking about here. These are my vertices, this is my vertex. So it could be a max or a min. The 0 is the x-intercept. And remember, we find that when the y is 0. And so if I have my quadratic shape graph doing this, I could have 2 of them. I could actually just have a scenario where there's only 1 0. So here's my 1 0. I could even have a situation where my graph is entirely above the x-axis and I have no zeros. So we're going to look at the example below, and this is going to relate back to the activity and the warm-up that you did today. So our example is an object is thrown upward from a height of 5 feet with a velocity of 60 feet per second. Its height, h of t, in feet after t seconds is modeled by this function. So they're giving us this equation. And if we think about what's going on here, let me go ahead and draw a graph. It's going to be a very crude looking graph. In your warm-up, we talked about how here's our ball, we're releasing it from a height of 5 feet, whatever it is, whatever I'm throwing, right? And we're throwing it up at 60 feet per second. But instead of going up 60, up 60, up 60, it doesn't really work that way, right? In real life, we've got gravity acting on this ball. And so the ball is going to go up quickly at first, and then it's going to slow down, and it's going to hit a peak. And then gravity is going to slowly overtake it, and it's going to go back towards the ground. So like gravity is acting on it the whole time. I guess I need to fix the way I'm saying this. But at some point, it's like gravity overcomes that initial velocity, and that's when it comes back to the ground. So the velocity of 60 feet per second is only good until about here, right? And then like gravity has completely overpowered it. It's going back towards the ground again. So let's go ahead and finish this graph here. I kind of want to erase this end on it. And I want to make it go all the way back down because I want to show where it's like touching the ground again, right? So like this is where I'd be launching it from. This is going to be my initial height. And this is where it's going to come back down and hit the ground. So what does the 60t plus 5 represent in the function? And that would be what the ball would be doing if there was no gravity. The height of the ball at time t if there was no gravity. Although if there was no gravity, we'd be floating around in the air too. There'd be all kinds of crazy things going on. But that would be that straight line we were talking about, that linear function. And so if we look at the 60t plus 5, the 60 is actually that velocity, that initial velocity. And the 5 was that initial height. What is a negative 16t squared? Represents the effective gravity. I do not like the way that's turning out. Let's make it look neater. The effect of gravity, which causes the ball and I'm going to say object actually because I don't know it's a ball, to slow down, stop, and start falling back again. Find the y-intercept of the function. So the y-intercept would be when I plug in 0 for t. So I'm finding h of 0, and I do that by taking negative 16 and multiplying by 0 squared, plus 16 times 0, plus 5. So when we take 0 and square it, I mean, this is just going to be 0. 16 times 0 is 0 again, and then we have that 5. So h of 0 is just going to equal 5. And what that represents is that initial height. So the y-intercept is 5. It represents the initial height. And I told you that up above too. So we are looking at, you'll often hear this called projectile motion, but we are looking at a very simplified form of it. So if you were to actually go and look up projectile motion somewhere, you're going to find that the formula is a little bit different. It just looks a little bit different than what we're doing here. We're doing a very simplified version. So it's a great introduction, and it's a great application of what a quadratic would be. But just know that it's not exactly perfect what we're doing. But it's a good Algebra 1 level introduction. So we have the graph of a function below. We want to know the x-intercept. What does it represent in this situation? So x-intercept means I'm looking for where we cross the x-axis. So my x-axis is here. It's labeled 1, 2, 3, 4. So I've got this little line between the 3 and the 4 that shows 3.5. And then somewhere between 3.5 and 4, I've got another mark. I'm going to say it's closer to 3.8 than 3.7, right? I think 3.75 would be halfway in between them, and it's a little bit beyond that. So I'm going to say that the x-intercept is 3.8 or 3.8 comma 0. So remember, it's that point on my x-axis, so my height is 0. And what does that show? It represents, and if this is projectile motion, it looks like distance above the ground. So it starts off here, it's going up, then it's coming back down. This must be when it hits the ground. It shows that after 3.8 seconds, the object hits the ground. And I mean, distance above the ground and feet and time, we've been doing all of these things where we're throwing an object up or something's happening. So I'm just going to assume that's what this one's about as well. What would be an appropriate domain? So domain is like your values for x. So what kind of x's do we have here? Well, we don't have any negative time. That would be weird, right? But our time starts at 0. and it goes all the way up to this 3.8 when it hits the ground. So it also doesn't make sense to look at like what's happening after 5 minutes, right? Like nothing's happening after 5 minutes. So our values for time, it makes sense to say that 0 is less than or equal to whatever our values are for time, which is less than or equal to 3.8. So that would be the domain for this function. So main ideas today, we're just kind of furthering this idea that we can describe situations with quadratics. And we're looking at, we call projectile motion again, but it is a very simplified form. The projectile motion equation doesn't look exactly like this, okay? And even with the 60 and 5, like those can be changed out, but it's a very simplified form. But it gives us an idea of a real life situation where you'd use a quadratic. We want to make sure that we go back and think about words like domain and range and x-intercept, y-intercept, what all of those things mean on a graph. So I like that we're continuing to look at that vocab as well. As always, if you've got questions, please make sure you ask.